Welcome, guys. In this video, we are going to study estimation for the binomial distribution. We'll start by looking for best point estimate for a binomial distribution parameter P, which stands for probability of success on each trial. And then we'll also build confidence intervals for that parameter B. And also we'll quickly cover on maximum likelihood estimation. So let's start by looking at the following example. Consider the problem of estimating the prevalence of malignant melanoma in 45 to 54-year-old women in the United States. Suppose that a random sample of 5,000 women is selected from this age group, of whom 28 are found to have the disease. Let the random variable xi represent the disease status for ICE women. So what's happening here is we have population of this age group, probability of success on each trial, P, this parameter P is unknown. In our case, P is, this is probability that randomly selected women will have malignant melanoma. Then we draw a sample of 5,000 women, and we find that 28 out of these women are found to have the disease. So we'll represent our women as random variables xi from x1 to x of 5,000. So each this xi represents a Bernoulli trial. So Bernoulli random variable, if you recall, Bernoulli random variable xi in our case is equal to 1 with probability of p, and is equal to 0 with probability of 1 minus p. Then if we sum up all these xi's, we'll get binomial random variable. So x here is binomial random variable with parameter n is equal to 5,000 and unknown parameter p. Okay, now question is, how can p be estimated? Our first logical guess would be use the following random variable, let's call it p hat, which is estimator for unknown parameter p here. Let's use sum of xi's over n as our point estimate for p. So basically, this is then equal to 28 over 5,000 in our case. Now, let's find whether this estimator is biased or not. So if you recall, binomial random variable x here, expected value of binomial random variable is equal to np, and variance binomial random variable is equal to npq, where q is the probability of failure, or q is equal to 1 minus p. Now, let's find expected value of p hat. Expected value of p hat is then equal, so this can also be represented as x over n. So expected value of p hat is equal to expected value of x over n. So this is 1 over n expected value of x, which is np. So this is equal to p. So we can see that our p hat is an unbiased estimator for p. Also, let's find standard error of that estimator. So variance of p hat is equal to 1 over variance of x over n. So this is 1 over n squared, variance of x, which is npq. So this is pq over n, meaning that standard error or standard deviation of p hat is equal to root of pq over n. So let's summarize our findings. Let x be a binomial random variable with parameters n and p. Unbiased estimator of p is given by the sample proportion of events p hat. Its standard error is exactly given by root of pq over n, and is estimated if we switch p by our estimator p hat by root of p hat q hat over n, where q hat is equal to 1 minus p hat. Maximum likelihood estimation. In this section, we shall develop a relatively simple method of constructing an estimator. It is called the method of maximum likelihood, and it was introduced by Ronald Fisher in 1912. Maximum likelihood estimation can be applied in most problems. It has a strong intuitive appeal, and it will often yield a reasonable estimator of your parameters theta. Furthermore, if the sample is large, the method will typically yield an excellent estimator of your parameter. And moreover, when sample gets large, your estimator will be unbiased, and maximum likelihood estimator will have smallest variance among all unbiased estimators. For these incredible reasons, the method of maximum likelihood is probably the most widely used one in statistics. Unfortunately, we are only going to slightly touch on the topic in this section. So let's start by considering the following example. Let's assume that you are tossing a coin, and you have a coin that is biased, but you don't know the probability of that coin landing on heads. Let's assume it is equal to P, and this is unknown to you. What you are going to do, you are going to toss that coin n times, and you will record them in those random variables xi, x1 through xn. Small xn's are outcomes of your tosses. These are equal to 1 if your coin lands on heads, and equal to 0 if it lands on tails. So basically, this is similar to the example we covered about malignant melanoma. So xi are our sample. Now let's find probability of obtaining this sample under an assumption that the value of your parameter is equal to P. So we are looking for probability that first random variable x1 is equal to x1, the second one is equal to x2, and xn is equal to small xn, under assumption that the value of our parameter, the probability that our coin lands on heads is given by some P. Okay, now since all these are independent tosses, we can split that joint density into the individual products. So this is probability that first coin lands on xi, given that x1, given that probability of landing on heads is equal to P, multiplied by probability that second outcome is equal to x2, given P, and so on. Now, what is the probability that first coin lands on x1, given that probability of heads is equal to P? This is P to the power of x1 multiplied by 1 minus P to the power of 1 minus x1. So for instance, if our first coin landed on heads, so x1 is equal to 1, then this term is going to vanish. So if probability of landing on heads is equal to P, then probability of that is P to the power of 1. All right, so second term here is P to the power of x2 multiplied by 1 minus P to the power of 1 minus x2, and so on. P to the power of xn, 1 minus P to the power of 1 minus xn. Okay, now multiplying, collecting all these P's, we'll have P to the power of a sum of those xi's multiplied by 1 minus P to the power of to the power of n, so sum of ones minus sum of those xi's. All right, so the probability that we defined above here, so probability of observed data given the value of parameter p is known as likelihood function. So in our book, it is defined in the following way. Other likelihood functions, the more common notation for likelihood function is a function of parameter theta, and theta is a parameter that we are trying to estimate. So in our case here, we are trying to estimate a single parameter p, probability of outcome of our coin toss. But in real world problems, in most cases, you would have several unknown parameters you will try to estimate, and we can represent p that we defined there as a vector now. So p will contain all the parameters, unknown parameters that you're trying to estimate. And x then is a vector of your observed data. So this function is known as likelihood function. In our case, we had a case when we had discrete random variable. If you are working with continuous random variable, your likelihood function will not change much. Instead of product of PMFs, conditional PMFs, you will have a product of conditional PDFs. So this is again from definition of from properties of joint densities. Similar argument as for discrete case, since these are independent random variables. Then if xi's are continuous random variables that are independent, then their joint PDF is defined as the product of their individual PDFs. All right, so finally, our next logical step is to maximize this likelihood function under the value of parameter p. So basically, we are looking the value of parameter p that is going to maximize the probability of obtaining the observed sample. To do so, we have to, in our simple case, we simply have to find derivative of our likelihood function, base dp, base our parameter p, and then find critical values and find the value of critical values that will maximize our likelihood function. In a multi-dimensional case, well, in most cases, it will be easier to maximize log of your likelihood function, since here we are working with products, and if you take log of your likelihood function, then you will turn these products into sums, and it will be easier to maximize log likelihood, log of your likelihood function. Since log, as you know, is a monotonely increasing function, then maximizing log of your likelihood function over parameter p will also maximize your likelihood function. But in our case here, we can simply take derivative of our likelihood function. So let's do that and find a parameter p that will maximize our likelihood function, and this value will be known as maximum likelihood estimator. Okay. So let's take derivative of that base dp. That will be sum by using product rule. We'll take derivative of that, product this, then derivative of that, product with that. So derivative of this term, base dp, is sum of xi's multiplied by p to the power of xi's minus 1, multiplied by 1 minus p to the power n minus sum of xi's, plus n minus sum of xi's multiplied by 1 minus p to the power of n minus sum of xi's minus 1 multiplied by p to the power of sum of xi's. Okay, now, so here we found derivative of our likelihood function base dp, which in turn is equal to, if we factor out p and 1 minus p, so p to the power of sum of xi's minus 1, 1 minus p to the power n minus sum of xi's minus 1. The things that will be left inside the sum of xi's multiplied by 1 minus p plus n minus sum of xi's multiplied by p. All right, now if we equate that to 0 and solve for p, okay guys, I've made a mistake here. When taking derivative of this term, we are taking derivative of that, so this is here, and I need to have minus in front there. So let's fix it. So I need to have minus here, then we'll have minus there. Okay, now let's solve this equation for p. Let's find root of this. We'll have sum of xi's minus p, sum of xi's minus np plus n sum of xi's, equate that to 0. So we'll have minus np, that should be p multiplied by xi, right? Okay, so those two terms will cancel out, and then p is equal to sum of xi's over n. Now, our p is defined on interval from 0 to 1. And then if you look at the signs of L prime, then you will see that this value is some value in between of 0 and 1. And your function will be, L prime will be positive here and negative there. So your function is increasing on interval from 0 to sum of xi's over n, and then decreasing. So at this point, you will have value of p that will maximize your likelihood function. All right, so this value here is known as maximum likelihood estimator. Now, in case when we are working with, let's say, likelihood function where there are several unknown parameters p, then you will need to maximize your likelihood function over those several parameters, and you would need to use techniques from calculus, extended techniques from calculus, Newton's method, or in case when we are working with multidimensional case, then you will also have some integrals, multidimensional integrals in your likelihood function. And those usually do not have in real world scenarios, they don't have closed form solutions. So you would need to use numerical methods to approximate your integrals. Some popular techniques, most popular techniques are sampling techniques like Monte Carlo Markov chain, also Newton-Raphson methods, maybe gradient descent, all other extended techniques from calculus, all other techniques, extended techniques from calculus arise in the case when you have a multidimensional likelihood function. All right, so our maximum likelihood estimate is given as sum of xi's over n, and as we said, this technique will give us unbiased estimator in case when n is large, and also This estimator will have a smallest variance out of unbiased estimators. And in fact, it's the same estimator as we found in our previous example. So our p hat was sum of xi over n, if you recall from our first example. So here we made a guess that we should try this estimator, and we have shown that its bias is equal to 0. So here is a formal definition of maximum likelihood estimator provided by our book. Suppose we have a probability mass function or probability density function that is a function of k parameters. The maximum likelihood estimator of the parameters p are the values that will maximize the likelihood. So MLE can be thought as the values of parameters that maximize the probability of observed data given parameters p. Okay, now we are done with point estimators. Now let's build confidence intervals. In the rest of this video, we are going to study interval estimation for binomial proportions using normal theory methods that are based on asymptotic assumptions that our sample size is large enough so that, for instance, we can use central limit theorem. So if we recall our first problem, we had population with unknown parameter p, and we draw our sample. Those are xi's. Sample size is equal to n. These xi's are Bernoulli random variables. Then our estimator p hat was equal to the average of this. So sum of those xi's divided by n. Then according to central limit theorem, if n is large enough, then p hat is going to follow normal distribution with mean the same as mean of population. These are Bernoulli random variables, and if you recall from one of our videos, mean of Bernoulli random variable is equal to p, and its variance is equal to p multiplied by q. And according to central limit theorem, then variance of x bar is going to be pq divided by sample size n. Now, if we standardize p hat, we subtract a mean, divide by standard deviation, then this random variable is a standard normal random variable with mean of 0 and variance of 1. Then we can finally build our confidence interval. We can set our random variable z to lie in interval between the following two critical values, z alpha over 2 and z 1 minus alpha over 2, where alpha, so this probability is equal to 1 minus alpha, and that, so we will build 1 minus alpha multiplied by 100% confidence interval. Okay, and now if we move on further from here, even if we substitute 1 minus p instead of q here, then expressing q explicitly in terms of other variables will not be an easy task. So what we are going to do is we are going to switch this term by root of p hat q hat over n. Now, so basically, yeah, we are making a lot of assumptions here, but if our sample size is large enough, then we'll get an adequate confidence interval. Okay, then multiplying every side of this inequality by this term, we'll get probability that root of p hat q hat over n, z alpha over 2 lies in interval. So this value lies in that interval. P hat q hat over n multiplied by our other critical value, z1 minus alpha over 2 is equal to 1 minus alpha. All right, now we need to express a p in terms of everything else. So we'll need to subtract p hat and multiply everything by -1. So we will end up by p hat. So that term will be on the left, p hat minus root of p hat q hat over n, z1 minus alpha over 2 less or equal p, less or equal than p hat minus root of p hat q hat over n multiplied by z alpha over 2. Okay, so probability of this is equal to 1 minus alpha. Okay, now we can switch this by that critical value, putting a negative sign in front. So this is plus then, and this is z1 minus alpha over 2. Okay, so finally our 100 multiplied by 1 minus alpha % confidence interval is given as p hat plus minus critical value z1 minus alpha over 2 multiplied by standard error, which is p hat q hat over n. All right, so here is the confidence interval for binomial proportions using normal theory methods. Now, in case when sample size is small, we can use exact methods that are provided in the chapter in the book, but we are going to skip this. We'll assume that everything is nice and simple and asymptotic assumptions hold. And on top of that, exact methods in practice, they are very, in most cases, they are inadequate since they will give you very wide intervals that are very, very practical. And if your n is large enough, then building confidence intervals this way for binomial proportions will give you very nice and adequate interval.